Hello everyone, my name is Wei from ANDIS. Today I'm gonna introduce about ANDIS ACE Solution on TWS Platform. TWS Platform has been on the market for a while, and many of the SoC design house has already rolled out couple generations of their SoC solutions. In this presentation, I will not only just talk about the ACE solution on TWS, but also give you a new concept of SoC architecture design. First, let's take a look at the performance results. In this application, we have designed 3 critical instructions for noise control algorithm and for some other Bluetooth routing job in the TWS platform. The first function, as you can see in this table, is FIR filter in 128 taps number. If we run FIR filter in pure C code, it will take around 1,600 cycles. But if we run it with customized instruction, it will only take around 128 cycles. So the speed up would be around 12 times. The second function is this mean square in 128 taps number. In pure C code, it will take around 1,800 cycles. In the customized instruction, it will only take 128 cycles. So the overall speed up would be around 14 times. The third function is quite special. It's a direct memory access function applied to TWS platform. The CPU cycle count of the function will depend on the SoC architecture. Normally, the heavier bus traffic it has, the more cycles it will cost. With ACE instruction, the tool has the ability to put the instruction have background attributes, which means the customized instruction can run in parallel with baseline instruction. In this scenario, the CPU can release more resources to do some other jobs. Finally, we applied all the instructions to the most complicated noise control algorithm called hybrid solution. If we run the algorithm in pure C, it will cost around 10,000 cycles. But if we run the algorithm with customized instruction, it will only take 250 cycles. So the speed up would be around 40 times. Here is the agenda for today's speaking. First, I will talk about TWS platform introduction, and next I will talk about ANDIS Wi-Fi role in TWS platform. Then I will introduce D25+ACE Solution. Next, I will give you an instruction about TWS ACE instruction. First, let's talk about TWS platform introduction. In the TWS platform, it should be cover several things. First, what kind of Bluetooth version is supported in the platform? It can be Bluetooth 4.2, 5.0, or even latest version 5.2. And next, what kind of Bluetooth technology is supported in the platform? Bluetooth low energy, single mode, or dual mode. Next one is the solution of active noise control supported in the platform. These 3 are the most common algorithm in the market, and hybrid solution is the most complicated algorithm. So it also costs the most computation power in these 3 of algorithm. And next, the platform should define what kind of interfaces are included in the platform. For example, as well as SPDIF, ADC or DAC, etc. And you will define how many analog microphones and how many digital microphones it will be supported in the platform. This microphone not only just being used for calling, but also being used for noise control algorithm. Okay, after give you all a brief introduction of TWS platform, next let's talk about the challenges in the TWS platform. First challenge I want to talk about is audio playback synchronization. Due to the separate 2 devices has 2 different crystals in the system, so the platform must to have a mechanism to synchronize the output of the PLL to make sure the 2 devices are running under the exact same frequency. Also, the 2 earbuds must have the same playback start timing. Second challenge is high computation requirements of noise control algorithm. in the noise control algorithm, it's not only just the high amount of computation, but also it requires low latency data paths for better noise control performance. The next challenge is audio codec support and audio formats conversion. Normally, when the Bluetooth system receives the data from the master device, the data format could be 16 bits little endian. And the device output interface may require a 24 bits big endian format. If we let CPU to run this kind of routine job, it will occupy a lot of resource from CPU. So in this case, we have made a customized instruction to solve the problem. Also, the TWS platform has to support different kinds of audio codecs, for example, LDAC, aptX, AAC, etc. Last challenge and also the most difficult challenge is computation and power trade-off. As I mentioned, not only just the noise control algorithm will cost high amount of processor resource, but also the audio codec will occupy the processor resource. And in fact, the noise control algorithm only needs a lot of multiplication and addition. So we have made the customized instruction to improve the whole system performance. It also needs a lower and high precision DAC and low latency ADC to have a better noise control performance. Next, I'll give you all a brief concept of TWS SoC design. Here is the SoC architecture, and now we have a bus matrix to connect all modules in the system. First, we have Bluetooth subsystem. It included RF, baseband controller, and memory dedicated for Bluetooth subsystem. Next, we have some analog macros and audio subsystem for audio data streaming. Next, we have an internal memory in the system. Usually, in this kind of tiny architecture, we just need a couple of SRAMs to be the system's memory. Then on the right side are some general IPs in SoC. We of course need a CPU, and it usually comes with an embedded DSP instruction. And we will have a standalone DSP to do some high amount of computation jobs, for example, noise control and audio codec. Next, we will have a hardware DMA to do some data movement and some format conversion. Next is some general IPs in SoC, like GPIO, I2C, RDC, and UART, etc. Next, let's talk about noise control in TWS platform challenges. It's actually not an easy thing if we want to run the noise control algorithm in a tiny system. In order to have a better performance, the system needs to achieve a couple of requirements. First is restrict latency for whole audio data paths. It's really important requirement for noise control algorithm. Once the latency is too high, the noise control performance will drop significantly. Next is real-time sample-based streaming. It actually just means if one sample in, then one sample out. I'll give you all an example later that you guys have an easier understanding. Next challenge is due to the tiny system resource is limited, but it still requires high amount of computation. Last, to have a better noise control performance, we need a low power and low latency and high sample rate ADC and DAC. Here is an example. If ADC and DAC sample rate is 192 kHz, it means one sample needs 5 microseconds. So the CPU clock is running under 160 MHz. So the algorithm should be finished in 800 cycles. So here I want you guys keep 800 cycles in mind, because in a later slide, I will use this number a lot to demonstrate some other concepts. Here is the example of noise control hybrid solution. For higher noise control performance, the higher filter tap number should be used. For example, under 128 taps filter, then how many addition and multiplication should be used? I will just give you the conclusion. The number is 896 additions and 896 multiplications for one sample. So if ADC and DAC sample rate is running under 192 kHz, the CPU clock is 160 MHz, so the algorithm only has 800 cycles for one sample. So if the feed-forward solution will take around 384 max for one sample, and the hybrid solution will take 896 max for one sample. So even though you have a really powerful DSP in your TWS platform, it's still impossible to let 896 max to be finished in one sample. That's why most of the TWS solutions are only capable of feed-forward and feedback solution. Here is the profiling result we have used under ND's IDE tool ND site. As you can see in this table, we have done two profiling results. The first one is FIR filter. It takes about 1,600 cycles. As you can see here, the self-cycle count is around 6,700 cycles, then divided by 4. And the second one is least mean square. It takes about 1,800 cycles. So as you can see here, the self-cycle count is around 3,600 cycles, and it's close 2 times. So just divide it by 2. You will get the number here. Both of the instruction over the limitation of algorithm requirements. That's why it's almost impossible to run the noise control algorithm in only one CPU platform. So you may think about just put the algorithm into hardware. You can have some advantages in this case, for example, parallel computing and optimized database, because all the design, you just design it by yourself. But you also will have fixed architecture and fixed algorithm and the complicated SRAM access. That's why the ACE solution we make the FIR filter and LMS to be our arithmetic unit. If you fully design in hardware, then it will lose the flexibility. If you run it with baseline instruction, it will cost too much power. Here, we introduce a ACE solution with high efficiency and flexibility. Next, let's talk about ND's FIR role in TWS. You may have already seen a lot of TWS platforms in the market. Those solutions normally come with two processors. It can be CPU plus DSP or DSP plus DSP. Usually one of the DSP will be used dedicated to some complicated jobs, for example, noise control or audio codec. But as I mentioned before, in fact, noise control only needs a lot of addition and multiplication. The full DSP for only compute noise control algorithm would be a lot of redundant logic in the SoC. That's why we introduced D25 plus ACE. In this combination, even the user needs some DSP calculation, we have provided RISC-V extension to do some specific formula. As for some routine job, the user can just define their instruction according to the system requirements. In this combination, you not only can have flexibility, but also you can have power efficiency. Then let's take a look at the system block diagram again. On the right side here is general solution for TWS. As you can see here is CPU plus DSP. Now we have introduced a new architecture which is D25 with RISC-V extension with 3 customized instructions: background FIR, background LMS, and background DMA. Next, I'll talk about D25 plus ACE TWS solution. First, let's have a timeline here. Then, let's put 6 samples in this timeline. As I mentioned, because now our CPU frequency is running at 160 MHz, and the audio sample rate is 192 kHz. So in each sample, we have 800 cycles to finish the noise control algorithm. In this timeline, we will make CPU to do some jobs, for example, DMA, audio codec, BT control flow, and some routine jobs. Next, let's put FIR filter for noise control. As you can see, only one of the arithmetic units has already over 800 cycles 2 times. Not to mention, we have put some other arithmetic units for noise control algorithm. So we introduced a ACE solution to let all calculation can fit into 800 cycles. In ACE solution, we have a strong ability to make the customized instruction to have background attributes, which means the customized instruction can run parallel with baseline instruction. Then, because the customized instruction has dedicated hardware, so the CPU cycles can drop from 1,600 cycles to 128 cycles. And next, the ACE has another strong ability called non-blocking, which means if you know the 2 instruction is independent, then you just let 2 instructions run in parallel. Then we can just smoothly run the noise control algorithm, and the CPU resource still has a lot of resource to do some other jobs. Next, let's make the timeline into 800 cycles. In this duration, we still need to do some other jobs, for example, audio codec, ANC control, BT control flow, and some mixed routine. Then we just put the customized instruction in the background. As you can see here, we have put 5 FIR filter and 2 LMS. With D25+ACE, we can achieve the most complicated algorithm without full hardware design. Here is the example we mentioned before. If the ADC and DAC sampling rate runs at 192 kHz and the CPU runs at 160 MHz, the algorithm should be finished in 800 cycles. But with ACE solution, we can achieve the most complicated noise control algorithm around 250 cycles. So even the sampling rate still runs at 192 kHz. We can still lower the CPU clock frequency to be around 80 MHz. And the lower clock cycles, it has more power to it saves in the platform. Here is the user have to design with the ACE framework. The user, as you can see, the user needs to define the ACE script here and the .bit file for RTO code. As you can see here, we have defined the data type as RAM for coefficient and audio data. And we defined 3 customized instructions: FIR calculation, LMS calculation, and BT DMA. After finishing instruction definition, then we just need to design the instruction core function in RTL. In a later slide, I will talk about the detail of the instruction and what the user needs to design for their customized instruction. Next, I will introduce the TWS ACE instruction. Here is the example of customized instruction for FIR filter in 128 TAPS number. This is the formula we need to implement. M stands for TAPS number, and W is coefficient for the filter, and X is the audio data. If we run the formula in pure C code, actually we just need a for loop to implement the formula. Then, as you can see here, is the hardware of customized instruction, and it can be separated into 2 parts. The first part, as you can see, is the block here. This is the block of customized instruction that the user has to design. In this block, we only need to put a multiplication and an adder and a flip-flop to accumulate the output result. And outside of the block, the copilot will just generate all the corresponding circuits. It includes the data memory, and you have defined in the script, and the control circuits that's connected to the CPU core. This is the block diagram of D25+ACE Platform. In this block diagram, because we need to support noise control algorithm hybrid solution, so we put 3 FIR filters here and 2 LMS instructions. The red block, the user can just integrate it by the standard SRAM interfaces. If the user wants to use the interface like AHB and AXI as their memory interface, the ACE framework is also capable of that. Let's have a review of D25+ACE performance. As you can see in this table, if we run the noise control hybrid solution in pure C, the speed up would be around 40 times. Due to we reduce the algorithm clock cycles significantly, so we can also drop the CPU frequency to 80 MHz or even to 50 or 40 MHz to save more power. So what we have today, so we introduced about TWS solution using this D25+ACE and a new idea of how to design an SoC. We also give you an introduction about ANC's FIR role in the TWS platform, and also give you an example of ANC customized instruction using ACE. Yeah, thank you all.